I'm Mohamed Salim Saddi. I work here at ENSTA as a PhD student, and I work also with CGG, an oil and gas company. And today, my talk is more about an application of interval analysis, about how we can localize receivers just using the phase. So first, I'll talk about the contractors, explain what a contractor is, just review it, as I think most of you know what it is. Then the motivation and the application of the problem, and then our contribution into solving this problem. So first, let's start with the definition of a contractor. Contractor as defined by Professor Jolin and Chabert in the contractual programming article. Is a mapping from Rn to Rn that has the three properties: contraction, consistency, and continuity. And you can look further into the definition on the article. But then I would like to define here again two types of contractors: an outside and an inside. The outside contractor is, let's say, we take a box X and the box Y, and Y is the contraction of the box X. So here, in this example, for example, we have an area that we are looking forward, which contains, for example, the solution, and we have the box X, which is the start box in here. And then when we apply the contraction, what we get is a smaller box around the area we're looking for. But this is like some kind of optimal contraction that we can go just around. But most of the time, it's not what we have. What we have is something like a box somewhere like this, and then we try to contract it. And if we contract it well enough, we can get a smaller box in this way. So this is an outside contraction. If we look now on what is an inside contraction, it's quite similar. But here we're not trying to find what's inside the contraction, but we are eliminating what's actually inside, not outside. So again, we have a start box, and then the contraction box is a smaller box where we eliminated every part of the maybe possible solution. So then I'll explain the phase equations and the problem and our motivations. So let's suppose that we have a source somewhere at coordinates bx and by, and emitting a continuous sign with a known frequency. And we have a receiver at the point px and py which is recording this signal. So what we can write the signal as follows: like S is a sine of 2 pi f t minus d over c, where t is the time, c is the celerity of the sound and of the signal, and d is the distance between two sources, and d is then written like normal distance between two points. So then the signal equation, if we write it as we know, and most of the things that we know, is written in that form. And then we have, let's suppose that the receiver has state equations and is moving in the space with the following state equation, where x is px and py, and a is velocity and the cosine the orientation, and the velocity sine the orientation of the target. So so here, yes, this is the problem. Then those are the equations, and we're trying to find px and py. We can measure here the velocity, the orientation, and the signal. So our motivation in here is to use interval analysis. Is instead of using Monte Carlo methods or other methods, is more to try to find a solution and being sure where the receiver is not in, and where the receiver may be in or is in this area. and which is something that is not really possible with most probabilistic methods. So here in this example, I will use the Euler discretization, like shown in here, and then the idea is to use a CBA-like algorithm. We will have a big box in the start. We suppose that the receiver is in. We put this box in a stack. Then we pick a box from the stack. We contract this box. If the contraction gives us a box smaller than the precision we're looking for, which is the width of the box, let's say, we will keep this box and we will not put it back in the stack. If not, we have to bisect it, split it, let's say just split it in two boxes, and put it back on the stack, and we'll run this algorithm until the stack is empty. So then, as the implementation, let's take again the same example. First we pick a box. Let's say it's this box over here. Then we apply an inside contractor, which means it will remove the parts that are inside the solution, the red box in here. Then we keep this one, because this one is the contracted one. Then we apply again the outside contractor. We remove this blue box now, and we have only the yellow box over here. And then we check the width. If the width is less than precision, it's okay. If it's not, we're gonna contract it again. And this is what we do here again. So this is the resulting box. Again, we split it on two. Take this one, outside contractor, we have the red box. Inside contractor we have the red box. Outside we have the yellow, and move over. So then what we have is a simulation. I'll make it work this time. It doesn't seem like it works. No. I have a video in me. So for this example, for example, I suppose that we have a source of the signal over here, and the robot is right here. It's just a dot now, because, and then we have the tail. So in the simulation, as you can see, from the start, I started contracting on all over this box, and in each iteration, because there's the time movement, because it's time lapse in here, I have all these boxes, and each time I work on all of these. So every single blue box, I'm 100% sure that there's no solution inside. The red box are a solution of the signal that I have recorded, which has a lot of noise. And the yellow box where I'm not sure the solution is. And as you can see here, those are some dots over there, and those are the buffer. Because what I do in this example, I take the signal and I keep the value that I have recorded. So first, I remember that I have recorded all the signals. So what I do is I have a forward-backward contraction. So I take all this box in the beginning. I make a forward contraction to apply every movement I did. Then I apply contraction on the signal I have and the signal received. And then I make backward contraction to get back to the possible solutions. So this is what I get. And here I have, this is why you see the buffer here. And the effect is more like a snake after that. Because here, and here again, I have a mirror. Because as the source is in here, I can be either doing this or doing this part, which have exactly the same signal. So we'll keep moving on. And then, here for example, I make a turn. But when I make a turn, I directly eliminate this what was possible target because I make this turn, and if I was in here, the equations are not verified anymore. because of the buffer actually. So again, I'll keep on moving. Then I make another turn, and here you see the buffer is moving because now I can't remember what I have been here on the start. All I can remember is that I have been here. So if I keep moving in here, we see something very strange here, which is actually not strange. But here again, what we see is that we are not sure anymore that if we are here, we have other possible solutions. This is because as I'm doing this movement, I can have done it from here and finish here, or here and finish here, and those are all the same. But again, if I go in time, I'll be able to eliminate them as I go just near the receiver. It's like if I have also implemented a Doppler effect, but without any additional equation. It's just the equation that we solve. Again, so as I continue, and you see, I will almost always have only one box. And again here, I do not contract only this box, I contract the full area. So, and the experience in here is pretty good because I'm moving pretty fast. Again, in this experience, the robot, it is the same robot recording the same signal, but the robot is not moving fast enough. So here, the robot cannot decide really where it is. And those are the same buffers, and as you can see, the space between them is not the same. And here is the source of the signal. So again, as I continue, I will never be able to eliminate this one, because, and even I have to create other one, because as I'm not moving quick enough, I cannot really decide where I am. Okay, so next, so those were the okay. So as a conclusion, as I have shown, the contraction, only using contractions, we have been able to eliminate and to solve this problem. And what we did also is that we implemented a new contractor called complementary contractor or sugar contractor, as it's always eliminates what's inside the solution. And then and we know that the inside contractor is not necessary, as all what we want to know is where are the possible solutions. So we can, to speed it up, we can only use one outside contractor, and we will get always all the possible solutions, even if some of the space is not, the contraction is not really in. So for future work, we are thinking of using a second receiver to be even more precise, and as we saw in the cases where we are moving not that fast. A second source maybe to again see if we can what we can get from it, and maybe add also an observer, as we saw, for example, for the first experience. At some time we have only one box, so instead of contracting all the boxes, we can always contract on the surrounding box, and then next time when we see new when the other possible will be the other solutions that will appear will not appear because the box is smaller and they will be outside the box, and the contraction will not contract them. So thank you for your attention, and if you have any questions, please ask.
Thank you very much for your interesting talk. Also, this paper is open for discussion. Let me start with the very first question.
Yes.
The state equations that you have shown were written as using coordinates.
Yes.
Why didn't you choose, for example, a polar representation?
Well,
simplify the computations?
No, actually in here we do not think about simplifying anything. Just think about the simpler equation that we can get, and to see how far can we get with how much results we can get with that.
Any questions from the audience?
Yes.
Yes.
I'm not sure I have understood why you have those ambiguity in the measurements, why you have two symmetric solution points at a given time.
Because in the let me get that. Because in here, what happens is I am recording a signal, and I know that my orientation is this way, and I'm having a speed. So being from the start, I know that I can be going somewhere in parallel in here, all over the space. So again, when I record the signal, I eliminate every other possible solution but those two, because they see the signal the same way. They observe the signal the same way. Unless I continue on moving, and at the end, around here, when I change my orientation, I can eliminate the other part, because this signal in here will not see the phase the same way as this one. So I don't have the other solution. Okay.
Okay, maybe one final question from my side. The observer that you mentioned, that we have, would it track some kind of region of interest around the possible position of the robot, or what do you think?
Okay, well, what I'm planning is, because in here, for example, this picture is perfect, because in here, for example, instead of me contracting again for all over this space, I know that I can be only in here, because this is what has been computed till now. So in the next steps, I will be always contracting just around here and not taking into account all the space.
That means tracking like some kind of region of interest
Exactly.
in the image process.
Yes. Yes.
Okay. And let's take our speaker again.